We previously introduced two types of stability: internal stability and external stability. Internal stability referred to stability of the equilibrium with respect to a change in initial conditions, and external stability referred to stability of the equilibrium with respect to an input. In our previous presentation, we derived a condition for external stability. The condition was for bounded input, bounded output stability, which meant that every bounded input produced a bounded output. This can be seen in the figure here. We have a system with input x of t and output y of t, and I'm showing bounds in red on x of t and other bounds on y of t. So if x of t lives inside bounds for all time, then y of t will as well. And the condition we had for bounded input, bounded output stability was as follows. A system will be BIBO stable if and only if the integral from -infinity to infinity of the absolute value of h of tau d tau is finite. So now that we have a condition for external stability, let's turn to internal stability. And the particular kind of internal stability we'll examine is called asymptotic stability. And what asymptotic stability means is that after a disturbance to the initial conditions, the system will return back to the equilibrium. This is a zero input case. We're looking at the response only to initial conditions here. So our model is q of d times y of t equals 0, since x of t will be equal to 0. For a linear system, the only equilibrium solution will be y of t equals 0. Now we know that the response to a disturbance to our initial conditions away from this equilibrium solution will be a sum of characteristic modes. For simplicity, let's examine the case where all the roots of the characteristic polynomial are distinct, lambda 1, lambda 2 through lambda n. The solution then, in terms of the characteristic modes, is y of t equals c1 e to the lambda 1t plus c2 e to the lambda 2t all the way through to cn e to the lambda nt. The output y of t will return to the equilibrium y equals 0 only if each one of these terms goes to 0 as time goes to infinity. So the condition for asymptotic stability is that each e to the lambda kt goes to 0. And you should begin to ask yourself the question, under what conditions on my characteristic values, lambda k, will each one of these go to 0 as time goes to infinity? Let's start to answer this question. We'll write lambda k in terms of its real and imaginary parts. So lambda k equals sigma k plus j omega k. In terms of this notation, it's clear that e to the lambda kt will go to 0 as t goes to infinity only if sigma k is less than 0 for every root lambda k. So that gives the important condition for asymptotic stability. The real parts of the roots must be negative. This condition holds because e to the lambda kt can be written as e to the sigma k plus j omega k times t, which can be separated to e to the sigma kt times e to the j omega kt. Since e to the j omega kt does not go to 0, we know that e to the lambda kt will go to 0 only if e to the sigma kt goes to 0. And e to the sigma kt will go to 0 only if sigma k is less than 0. So this brings us to our final result. The system model q of d times y of t equals p of d times x of t has internal asymptotic stability if and only if all characteristic values lambda k have negative real parts. Now the way this is typically represented is by plotting the lambda k in the complex plane. The requirement, then, is that all of the lambda k must be in the left half of the complex plane. It's critical to point out that it has to be all of the lambda k. If even one characteristic value is not in the left half plane, we will not have asymptotic stability, because then there'll be one mode which will not go to zero as time goes to infinity. Also, the lambda k's must be in the left half of the complex plane. They cannot be on the imaginary axis. They must have negative real parts. When we developed this idea, we assumed that all the roots were distinct. It turns out the case of repeated roots is not any different, so the condition is not any different. For asymptotic internal stability, all roots must be in the left half plane, whether they're simple distinct roots or whether they're repeated roots. What if a system does not have asymptotic stability? What does that mean? It turns out there are two cases, which we'll study. The first is internal instability. If the characteristic polynomial q of lambda has one or more roots, lambda k, that have positive real part, then the system is said to be internally unstable. This means one of the modes goes to infinity as time goes to infinity, and it goes to infinity in an exponential fashion. We can give two examples. The first is lambda k equals 1, so we have a real positive root. In this case, the mode is e to the t, and you can see it blows up to infinity as time goes to infinity. The second case is lambda k equals 1 plus j times 2. The real part of this is positive, and so while it oscillates, its amplitude increases exponentially. Now note that I said that if the lambda k had positive real part, then we had internal instability, but not if and only if. So this is a sufficient condition, but not a necessary condition for internal instability. In other words, there is another case where we have internal instability. So here is our sufficient condition for internal instability. It is that one or more roots of the characteristic polynomial are in the right half of the complex plane. I said that there were two cases if the system was not asymptotically stable. The first of these was instability. The second is marginal stability. Now this is different than asymptotic stability. In this case, the response to the initial condition does not go back to zero, but it does stay close. So clearly this is not an asymptotic stability. It's also not exponential instability. When will this occur? If all roots of the characteristic polynomial are in the left half plane or on the imaginary axis, and all those on the imaginary axis are not repeated, then we will have marginal stability. In this case, some of the modes decay to zero as time goes to infinity, and others do not. The ones that do not remain bounded, however. These modes do not blow up to infinity as time goes to infinity. Here is a concise explanation of this result. Any roots in the left half plane correspond to modes that go to zero. For example, if lambda k is minus 1, the mode is e to the negative t, and that goes to zero as time goes to infinity. Distinct roots on the imaginary axis correspond to modes that do not blow up with time. For example, if lambda k equals 0, we know the mode is e to the 0 t, which is 1, a constant. So that does not increase to infinity as time goes to infinity. However, Repeated roots on the imaginary axis yield modes which have a t in them, and these modes do blow up, although not exponentially. They blow up polynomially in time. So for example, if we have lambda k equals 0 and lambda k plus 1 equals 0, we have the modes e to the 0t, which is a constant, and te to the 0t, which is t. That will blow up to infinity as time goes to infinity. This is why we cannot have repeated roots on the imaginary axis for marginal stability, but we can have distinct roots on the imaginary axis. So we've now discussed three different conditions. We had asymptotic stability, marginal stability, and instability. And we've had a number of conditions, and sometimes it can be hard to keep track of these. So here is a summary of all our results for internal stability. First, we have asymptotic stability, and this corresponds to all roots in the left half plane. They do not need to be distinct. They just need to be in the left half plane. The second case is marginal stability, and for marginal stability we need no roots in the right half plane, and any roots on the imaginary axis must be distinct. And the third case is instability. This requires at least one root in the right half of the complex plane, or repeated roots on the imaginary axis. The results we've had here for stability and instability have pointed to an important fact, that is that the root locations of the characteristic polynomial are associated with particular modal behavior, and we can try to understand the behavior of a system by looking at the roots of the characteristic polynomial. Where the characteristic values are in the complex plane determines the shape and characteristics of each mode. Let's consider several different cases. Our first case concerns modes which have characteristic values in the left half plane. Two types of modal responses exist in this case. One corresponds to real characteristic values, the other to complex characteristic values. The first one, associated with real characteristic values, is shown in the lower left. We have simple exponential decay from the initial condition. The second, the complex characteristic value case, is shown in the upper left. The amplitude is decaying exponentially, but also oscillating. The next case we'll consider is the one where the characteristic values are on the imaginary axis. Again, there are two possibilities. The first is that the characteristic value is at the origin. In this case, the mode is a constant, as shown in the lower left. The second possibility is that the characteristic value is imaginary. In this case, the modal response is a sine or a cosine signal. We'll now consider the modal responses that occur when the characteristic value has a positive real part, that is, it's in the right half plane. As before, there will be two possibilities, one corresponding to a real valued characteristic value, the other corresponding to a complex valued characteristic value. The real valued characteristic value is associated with a mode that grows exponentially. The response with the complex characteristic value in the right half plane corresponds to a mode that also grows exponentially. However, it oscillates as it grows, as shown in the upper right. Let us close by looking at the repeated roots case. There are two scenarios we'll consider. The first scenario is repeated roots on the real axis in the left half plane. With these roots, we'll have two modes, e to the minus t and te to the minus t, as shown in the lower left. Our second scenario is two roots at the origin. In this scenario, our two modes are a constant and a ramp, as shown in the lower right. You should familiarize yourself with the various kinds of modal behavior that are associated with different spots in the complex plane. This material is very important for you to understand much of what we'll do later, especially time response. If we have asymptotic stability, we know all the characteristic values are in the left half plane. And in this case, each mode, e to the lambda kt, will go to 0 as time goes to infinity. Furthermore, we can show that the integral from minus infinity to infinity of the absolute value of e to the lambda kt will also be bounded. Now, since the impulse response is the sum of the characteristic modes, we will also from this have the following result. The integral from minus infinity to infinity of the absolute value of h of tau d tau will be finite. This is the condition for BIBO stability that we had before. So you see, if we have asymptotic stability, we will also have BIBO stability. This is quite significant, and you should be sure to remember it. Asymptotic internal stability implies BIBO stability. But is the reverse true? Will BIBO stability imply asymptotic stability? The answer is usually, but not always. So we can't count on BIBO stability implying asymptotic stability. The relationship does not go both ways. So when does a system have BIBO stability, but not have asymptotic stability? We alluded to the answer to this before. We said that if the system had hidden modes, it would be possible to be BIBO stable, but not to be asymptotically internally stable. So the issue is hidden modes. That is, modes that do not affect the output, or modes that are not affected by the input. Such modes would not affect the impulse response h of t, and therefore would not impact BIBO stability. But if these modes did not decay to 0, then the system would not be asymptotically stable.